Our lecture today is about harvest and conservation. It is based on chapter 32 of Villalobos and Ferrere's Principles of Agronomy for Sustainable Agriculture. First of all, let's consider that probably harvest was the first thing that was invented before actual agriculture. Tribes of hunter-gatherers were collecting seeds from grasses all around to supplement their diet, which was based on hunting and collecting fruits and seeds from natural vegetation. These seeds were converted to bread and ale, so humans were able to exploit seeds from grasses long before they cultivated them. One main advantage of seeds was that they could be stored for long periods, which didn't happen with other sources of food. However, the collection of seeds had a very low efficiency because they were scattered among other plants that maybe could not be used. That probably favored the invention of agriculture by thinking about how good would be to concentrate the useful plants in specific areas. The objective of harvest is to obtain useful products or materials. It is the final stage of the crop cycle, and it is the main objective of agriculture. In traditional agriculture, harvest was performed using labor with the help of beasts of burden. That meant that, for instance, 1 hectare of wheat could require around 130 person-hours, and that limited the land that could be cultivated. For instance, if 45 days of 10 hours per day were available for the harvest period, one person could only harvest 3.5 hectares. That contrasts quite a lot with modern agriculture, where mechanized harvest has allowed the reduction of human labor required for harvesting operations to around 0.4 person-hours per hectare of wheat. We might harvest whole plants or only parts of the plants. The time and the method will depend on the use of the crop. Let's remember the concept of physiological maturity, which is the time when the harvested organ reaches its maximum biomass. However, usually it is not interesting to proceed to harvest at physiological maturity. We have to wait some time for the conditions being better for the harvesting operations. That time would be called harvest maturity, and it is always later than physiological maturity. Apart from harvesting, we may need to perform other operations before harvest, like preparing the crop, like applying the foliants, promoters of abscission, or preparing the soil, like compacting or irrigating. After harvest, we may require drying of the grain, cleaning, removal of some parts, or sorting. In this table, we have classified the uses of crops on the left hand of the table and on the harvested organ on the right side. Crops might be used for food, either as a fresh product or for transformation, for fodder, or for producing industrial products in the textile, chemical, fuel, perfumery and cosmetics, and pharmaceutical industries. The use of the crop may be to produce seeds and propagules for other farmers. According to the harvested organ, we may be collecting shoots, and in that case we may collect vegetative parts, but more typically we will collect reproductive organs like flowers, fruits, or seeds, and in some cases more specific organs or products like sap, for instance in maple, latex like in rubber or opium, and resins, for instance for pine. If we collect subterranean organs, we might be harvesting roots like beet or carrot, bulbs like onion, tubercles like potato, or rhizomes as ginger. Harvest operations are quite variable and could be just mowing, like in the case of forage crops or medicinal crops. Reaping, threshing, and winnowing would be the method of harvesting for cereals, pulses, and oil crops. Combing and pulling for fruits. Digging, sieving, and loading for tubercles and roots. Cutting for vegetables. Gathering for fruits. Shaking, sweeping, and loading for nuts and olive trees. In general, the amount of biomass that we will collect will be less than the actual yield. In other words, the collected yield is lower than the physiological yield. This is due to losses, and that those losses might occur before harvest due to respiration of the harvestable organ that is proportional to the water content and temperature of the organ, or to the loss of harvestable structures due to the dehiscence of pods, abscission of fruits, consumption by herbivores, or the occurrence of accidents like fire, hail, etc. We might have yield losses during harvest process. For instance, we might have inaccessible parts of the plant, for instance plant parts below the cutter bar. We might have parts of the plant that are not caught by the harvest system or dropped by it. The harvesting system might deteriorate the structures collected, for instance broken grains, damaged fruits, or we might reject part of the harvest due to low quality. Some cases, part of the yield may be left uncollected due to poor quality or excessive harvest cost. We might also have losses after harvest. Those will occur during packaging, transport, or storage. That include the respiration of the harvestable organ that depends also on the water content and temperature. They can be caused by consumption or deterioration by insects and fungi, and they depend on water content and temperature of the product and relative humidity in the storage facility. After harvest, we might also reject part of the harvest due to quality criteria. If the collected product does not fit quality criteria, we might just reject it, or we might require an additional cost for its separation. Harvest also interacts with other operations in the farm. First of all, harvest usually requires labor that cannot be dedicated to other operations in the farm. But the date and method of harvest will determine the possible choices for the next crop in the rotation, as they will determine how long it will take between harvesting and the preparation of the field for the next crop. Also, the method of harvest determines the amount and distribution of the residues. We may need additional operations for management of the residues like burning, chopping, or removal. And that will affect also the time required for land preparation for the next crop. Other techniques like irrigation or tillage or pesticide application might interact with harvest. We might apply irrigation to improve the soil conditions before harvest, for instance, before digging of potatoes. Or we might stop irrigating before harvest, sometime before harvest, to promote abscission and prevent soil compaction due to the traffic of machinery. In some cases, we might perform some tillage operations before harvesting, like soil compaction. And of course, pesticide treatments will be stopped long before harvest according to the safety period of the pesticide. Let's consider first the harvest of grains and seeds. In principle, grains can be stored safely when they are harvested, clean, dry, healthy, intact, and cold if possible. Usually, that requires to wait after physiological maturity for some time, basically to allow the grains to dry. But waiting for the grains to dry has some other effects. We will increase dry matter losses or reduce grain quality. We will increase seed losses. We will also have a higher risk of accidents like lodging, hail, or even risk of fire. Apart from that, if we wait, we will increase the risk of mycotoxins. Mycotoxins are toxic chemicals produced by naturally occurring molds and some pathogens like Fusarium. The most common mycotoxins are aflatoxins that are generated by molds of Aspergillus flavus and Aspergillus parasiticus. The probability of contamination with aflatoxins is higher when harvest is delayed during wet weather or when grain is harvested wet and drying is delayed. Water-stressed crops are more susceptible to infection. Aflatoxin production does not only affect cereal grains but also other products like sunflower seeds, nuts, cassava, cottonseed, spices, pepper, hay. On many occasions, the seeds are collected before they are dry enough for storage, so they will require drying out of the field. In those cases where pod shedding is an issue, for instance like in rapeseed, or when the time for harvest is limited, the harvest might be performed in two stages. The first is swathing. In other words, cutting the crop and leaving it forming windrows where it will dry for between 5 and 10 days or even more. After that, when the cut crop is dry enough, we will combine, and that will separate the seeds from the residues. Here we see an example of swathing of canola. The arrow marks the direction of the machine, and the machine leaves behind the windrow that will facilitate the drying of the plants. The second stage is when the plants are dry enough, we will use a combine for separating the seeds from the residues. The main factor affecting a successful harvesting is the water content of the grain, as it affects the risk of physical damage of the grain during harvest, the activity of insects and fungi, and the metabolic activity of the seed, which in turn affects the rate of deterioration of the seed, the release of oxygen by respiration, and the heat generation in the stock later in the storage facility. In this table we see for different values of water content the corresponding water potential, the seed status, the activity of biotic factors, and the degradation under storage. When the seeds are dry, we have, for instance, from between 0.10 and 0.13, we have still activity of insects, but the degradation under storage is low. And for even drier seeds, the activity of both insects and fungi will be very low, and the degradation under storage will be low. It might increase when the temperature is very high. But consider that physiological maturity implies a much higher water content. That is why we need to reduce, to go to the lower part of this table, for the conditions to be better for harvesting. After harvest, when seeds are taken to the storage facility, they will reach a water content that will imply an equilibrium of water potential between the seed and the air outside. The water potential in the seed can be calculated according to the conditions outside using this formula, where R is the gas constant, T is temperature, MW is the molar mass of water, and RH is the relative humidity. So for a given air temperature and relative humidity, the grain will reach a given potential, and that implies a given equilibrium moisture content. This is important because it will determine if the seed dries or not. Some seeds, called orthodox, which are most of the species, can be dried to very low water content without being damaged. In some cases, however, the so-called recalcitrant seeds might be killed if desiccation occurs. That happens with the acorns of Quercus species, oil palm seeds, chestnut, and cacao. Here we see the relationship between seed moisture on a fresh basis and relative humidity in the air outside. These curves are called seed moisture isotherms. Here we have the black line for wheat and the red line for sunflower. That illustrates that the seed moisture isotherms change basically due to the oil content. So, for a given relative humidity, the seed moisture content will be much higher when the oil content is low. If we consider values around 70% of relative humidity, that means that the water content in the seeds might be from around 14 for wheat to around 8% for sunflower. In this table, we report values of water content for different seeds at physiological maturity, when the seeds are suitable for harvest, or the recommended water content for harvest, when no air drying will be performed, or when air drying will be performed. Here we also can find values of long-term values of water content for long-term storage. They are typically below 15%, and they are lower for oilseed crops like rapeseed or sunflower. On the other hand, for cereals, the values are between 12 and 15%. Seeds might lose viability, and this loss of viability is proportional to the water activity, in other words, to the relative humidity outside. This loss of viability is proportional in the range from 0.1 to 0.9, from relative humidities of 10 and 90%. In general, the rule is to keep relative humidity between 67 and 70% below those values to prevent germination of spores of fungi. If required, we might use conditioning systems that can be classified in aeration systems, systems with natural air drying, low temperature systems that allow heating between 3 and 7 degrees the air, and high temperature systems. In summary, we have seen that the harvest of seeds basically depends on the water content of the seeds that might require drying after harvest. In the case of forage crops, we first have the alternative of direct consumption by grazing animals. We can have grazing during specific growth stages in the so-called dual-purpose crops like cereals or rapeseed that can be grazed during vegetative growth because meristems are not affected, so crop growth will resume afterwards and lead to seed production. We can also graze the stubble of the crop after harvest. For forage crops, usually the alternative is to try and conserve the harvested forage using different methods like silage, where storage is performed, harvest is performed with water contents between 50 and 65%, haylage with between 30 and 50% of water content, and hay between 15 and 25%. The best nutritive quality of forages usually occurs around flowering time, so mowing later will mean a higher production of biomass and drier biomass, which is good for conservation, but with lower quality. The conditions after mowing also must be dry enough for successful drying of the crop, mostly if we're going to use haylage or hay for conservation. Silage consists of cutting, chopping, and taking the crop to the silo, and then compact it to exclude air, and then seal it with plastic to ensure anaerobic conditions. Those are required for lactic bacteria to thrive and reduce the pH, that in the long term means conservation of the product. Some crops are left in the field during a couple of days before silage. That is not the case with maize, which might be taken directly to the silo. In the case of haylage, they are left longer in the field, the crops, after mowing, for drying, and then they are wrapped tightly in plastic-covered bales. For hay production, we require a longer drying period, but in any case, we have to minimize the duration of that period to reduce respiration losses. The time required for drying is proportional to total biomass, and it is inversely proportional to swath area and ETO, the evaporative demand. The hay production has different operations. First, mowing and sometimes conditioning. And conditioning means crushing the material to speed up drying. Then we might require tedding, which is mixing and upturning the cut forage. And then windrowing, is piling the plant material in rows for increasing the speed of drying. Finally, we will proceed to baling. This is a machine mowing alfalfa for producing hay. Here we see the cut plants. And here is the final product of hay, which is the bale. In the case of underground organs, we have tubers like potato, yam, roots like sugar beets, turnip or cassava, and bulbs like onion or garlic. In general, the idea is to harvest around physiological maturity when green area is small. In some cases, we may advance harvest, for instance, for potato, if the prices are high enough. The removal or killing of the shoots before harvest is positive as it enhances periderm thickening of tubers, which reduces the risk of peeling or bruising during the harvest procedure. In the case of carrots, the harvest will be performed when the size is adequate for the market. The operations required for harvesting underground organs are cutting of the shoots, digging of the subterranean organ, and lifting. We might clean and transfer directly to the trailer from the harvesting machine, or we might leave the produce in the field for further drying. As opposed to seeds, in the case of underground organs in storage, we have to prevent desiccation. As water loss is proportional to vapor pressure deficit, we will reduce desiccation by applying cool, moist air, almost saturated. Here we see a picture of a potato harvester that cleans and lifts and transfers directly the clean potato to a trailer. In the case of fruits and vegetables, we might think about first producing for the fresh market, in which case usually we collect by hand when the fruits have reached the desired size and are approaching ripening. For wine grapes, there are other quality criteria to use related to the sugar content or to the color as required by enologists. And in the case of olive oil, we might harvest earlier to get higher quality oil and better prices, but at the cost of having a lower oil content and therefore a lower yield. In the case of fruits, it's important to consider the difference between species in the production of ethylene for ripening. We can classify crops of fruits in climacteric and non-climacteric, which are those that produce ethylene and therefore can ripen off the plant after physiological maturity. That is the case with most fruits. So they can be harvested at any time after reaching good size and ripened later. But they can also be harvested when fully ripe. So we have more options with climacteric fruits than with non-climacteric fruits. The later, non-climacteric fruits, for instance citrus, strawberry, watermelon, have to be on the plant to complete ripening. So harvest must be delayed until full ripening. In the case of fruits for processing, for canning, for drying, for producing preserves, for oil extraction or for juice, we may mechanically harvest when the fruits are ripe. In the case of nut crops, we will harvest after physiological maturity, taking into account that if we wait, we will decrease the water content, which is good for conservation, and we will help in the formation of an abscission zone that promotes fruit detachment at harvest. However, delaying harvest has the risk of increasing fruit drop, which increases the cost of harvesting. Here we see a shaker for collecting almond trees. The inverted umbrella serves to collect the drop fruits. And here we see an oil harvester in a superintensive olive orchard.